Does this work? This is red. All right, thanks. Okay, then welcome to our last class this semester. Are there any questions concerning the class from Tuesday, linear programs? Just turn on. Okay. Any questions? Everything clear? Very good. Because then I'm going to start the last topic of this class, which will be NP and computational hardness. And I'll start with this motivation. So let's say you do really good in this class in Computer Science 465. You graduate and you get your dream job at Google or Microsoft or wherever it is that you want to work. And your task is to come up with an efficient algorithm for a really hard problem or seemingly hard problem. And you're trying very hard for many weeks and months, and you know that you have a meeting coming up with your boss and you have to tell him that you somehow failed. And you're thinking about what the right strategy will be to explain your boss that you failed without really saying that you failed, such that you could keep your job. So one way is to be sort of modest and tell him, well, I can't find an efficient algorithm. I guess I'm just too dumb. That would be one possible strategy, and most likely you would lose your job. So probably not advisable. A second strategy is you could say, well, listen, I can't find an efficient algorithm because no such algorithm is possible. No such algorithm exists. That would be nice to say. But again, it's a bit, or in this case, it's a bit brave because you would have to argue why that's true. And you have to prove that no such algorithm exists, which is typically a very difficult thing to do. It's typically difficult or generally difficult to prove that something does not exist. So the third strategy would be to say something like, I cannot find an efficient algorithm, but neither can all of these famous people who have tried before. You can see there's many of them. And this might sort of convince your boss because there's really a lot of famous people who tried before. And yeah, since you had a similarly hard problem, you're not doing it worse than all these famous people. So maybe that helps you saving the job. So in a way, you want to say something like, my problem X that I'm trying to solve here is at least as hard as some problem Y And problem Y has been studied by many, many clever people, and they have failed to come up with an efficient algorithm. And since my problem is at least as hard as their problem of all these famous people, this is a good reason that I sort of failed. I cannot prove that no efficient algorithm exists, but I didn't do worse than most of these very famous people. So that's what we're trying to find out today, how we can do something like this. So in case you do fail to come up with an efficient algorithm, what will you have to do to make your boss not happy, but at least to convince your boss that you not necessarily did a very bad job. And so the first ingredient we need for this is what we call a polynomial time reduction. And the idea of a polynomial time reduction is that you're trying to come up with an algorithm for problem Y. So you have an instance for problem Y. You have, let's say you want to find the shortest path in a graph. This is maybe problem Y, and the instance could be some graph and some vertex S from which you want to find shortest paths in your graph. You don't know how to solve Y, but you know how to solve a different problem, X. And so you're trying to reduce your problem, the shortest path problem, to some other problem that you know how to solve. So you could start by trying to pre-process this input, your graph, in which you want to find the shortest path, to make it suitable as input to another problem or to another algorithm that solves another problem X. We do some pre-processing, and we spend only polynomial time in this pre-processing. So we don't waste too much time in sort of converting this instance. We really want to do this efficiently. So we only spend polynomial time in pre-processing this instance to problem Y. And then we feed this pre-processed instance into an algorithm that is designed to solve problem X. And you don't do this necessarily only once, but you can do this many times. More specifically, you can do this polynomial many times. So again, you don't want to spend too much time, but you can sort of use this algorithm that is designed to solve problem X a polynomial number of times. And so you're running this algorithm then as a black box, this algorithm for problem X on your preprocessed instance. And then again, you're spending a reasonable amount of time, meaning a polynomial time, into collecting all the results from this algorithm X. Again, try to convert this result to a result finally for your problem Y. So this is basically how your algorithm for problem Y works. You just convert the input a little bit, make it suitable for algorithm X. You call X a bunch of times, then you collect all the results from X and make a solution for Y from that. So this is the picture, and this is sort of the more formal definition of polynomial time reduction. So we call a problem Y polynomial time reducible to a problem X, which you denote here in this notation as Y smaller or equal than X. If there exists an algorithm that solves any instance of Y making polynomial many elementary operations, so this is the pre-processing and the post-processing, and polynomial many calls to a black box solving X. This is shown here. Okay, so this is what's called polynomial time reducible, and we'll see examples. But let's first think about what this means, what kind of consequences this has. Because now if I have a problem Y that can be polynomially or reduced into X in polynomial time, then if X can be solved in polynomial time, what statement can you make about Y? Any suggestion? So I'm reducing Y to X using that scheme that I've just shown, and I use a black box that runs in polynomial time. What is the running time of Y? It's again in polynomial time, so I can solve Y in polynomial time. And why can I do that? Because in every step we required sort of a polynomial time investment. Because we first had the polynomial time in the preprocessing, then we call the algorithm for X a polynomial time. Each time spend the polynomial time in solving X, and then again spend polynomial time in post-processing the output. So the overall time will be maybe a very large polynomial, but it's still a polynomial in your input. So by reducing Y to X, you basically solved y in polynomial time using a polynomial time algorithm for x. And we have done this many times. Can you remember? Can you recall any example where we have done something like this? Yeah. That's one way. Yeah, that's a good example. I didn't think of that. So in this case, it's a more general platform because the Metroid is sort of a more general framework, and we had to transform sort of the input. I mean, an MST problem is sort of a graph problem. So we had to change the weights to fit it into that framework. It's true. So this is one example. Another example. Yeah. Longest increasing subsequence, which we reduced to what? A longest path in a DAG. Exactly. Good example. So when we try to find the longest increasing subsequence, we reduced it to a longest path in a DAG because we introduced nodes and we had edges whenever. So we have a permissible transition between integers. And in this resulting graph, we then just computed the longest path. And then from this longest path, we could read out the longest increasing subsequence. So these are two examples. There's, I think, a couple of more. Bipartite matching, for example. We solved bipartite matching by reducing it to a maximum flow problem. If you remember that we had sort of a bipartite graph, and then we introduced these artificial nodes for source and sink, and we introduced edges with capacity 1. And so this is basically what you consider as the pre-processing. Then you solve a maximum flow problem. This is your algorithm, using any algorithm for Falkeson. And so you use this maximum flow basically as a black box for solving x. And then from the result of maximum flow, you could read out a solution for the bipartite matching because you have this disjoint paths, and whenever there's sort of a path connecting two vertices in your bipartite graph, you include an edge in the bipartite matching. So this is how you basically transform the output of maximum matching to an output of an output from maximum flow to an output of bipartite matching, which again took only polynomial time. So in this the one specific difference here to the more general form is that in these examples we have sort of some polynomial time preprocessing because we generated sort of this, for example, a network for a maximum flow, which took polynomial time in the size of the graph. We called the algorithm only once, so it's a polynomial many times, but in this case, we only called it once, the maximum flow. And then from the maximum flow, with some post-processing, we derived a solution for bipartite matching. In this sense, if I think about it, it's a bit tricky to consider the Metroids as such kind of reduction, because this is more like a mathematical framework that we used to capture this description. We didn't have a specific algorithm at this point for Metroid. We did use a greedy algorithm, but it turns out that the greedy algorithm actually was nothing else than solving the minimum spanning tree. So maybe that's not such a good example to think of this. But these three examples, they definitely fit this pattern where you first preprocess your input into an instance of another problem, solve it with some black box, and then just do some post-processing to get the result for the original problem. So this is what we did so far, but it's not really what we're interested in today. We're interested in sort of the reverse. So if, again, y can be reduced in polynomial time to x, and if I cannot solve y in polynomial time, what can I say about x? Yeah. X cannot be solved in polynomial time because if I could, again, this would mean that I can solve y in polynomial time. So this is just the counterpositive of this one here. It's nothing different. But if I can reduce y to x and I cannot solve y in polynomial time, that means I also cannot solve x in polynomial time. And this is the way we see it as, that one problem is at least as hard as the other problem. Let me just finish this. Yeah, so then x cannot be solved in polynomial time. And I want to give you an example now of this. So how does such a reduction look like if it's not such a trivial example as we had before with polynomial time algorithms such as max flow? And for this, I want to give you an example using two problems that we have not talked, or at least for, I mean, one problem seems to be new to you, independent sets. Have you heard of independent sets before? Did we talk about this in this class? I don't think so. But in any case, I'm going to introduce independent set. So you want to introduce a reduction from one problem to another, and one of these two problems will be the independent set problem in a graph. So the independent set problem is given a graph. You want to find a set of vertices that are independent in the sense that no two of them are connected by an edge. So this is just a formal definition. Let me just show you an example. I think it's getting clear. So here's a graph is for vertices, and let's say I'm picking the two red vertices here and here. Does this form an independent set in my graph? So these two red nodes, according to this definition, are these two nodes independent? No? Any suggestion? We said a set of vertices is independent if no two of them are connected by an edge. So we only have two. Are they connected by an edge? No, they're not connected by an edge, and that's why they're independent. So this is an independent set, right? So these two are an independent set, right? In contrast to this one here, if you pick three vertices now, the three red ones, again, the question, are there any two vertices that are connected, I mean, selected red nodes that are connected by an edge? Yes, in this case, these ones are connected by an edge, and also these ones are connected by an edge. So this is a set of nodes that would not be independent. And therefore, the answer to this case is no. Okay, is the definition of independent set clear to everyone? Okay, so in the maximum independent set problem, we are given a graph G and a number K. And in the decision version of this problem, we're asking if G contains an independent set of size K. So this is called the decision version because we are answering this with a yes or no. So we're not explicitly trying to find the maximum K. This is the kind of problems that we have studied so far in this class. We always looked at optimization problems. We tried to find, for example, the maximum or the minimum independent sets. There's also a variant of this problem, an optimization version, where we're trying to find the maximum independent sets. In this class, in terms of computational hardness, we're dealing with the decision versions of these problems. So the decision version, so this is maybe more familiar to you, this kind of problem, find the maximum independent set. Here we're saying we have this additional input K, and we want to decide if our graph contains an independent set of size at least K. Now, how is this really so different from the optimization version? Not really, because we can reduce in polynomial time the decision version to the optimization version. Let's see if we understood the concepts. Can someone explain to me why I can solve the decision version with an algorithm that solves the optimization version of this problem? Yeah.
But have an overall effect on a lot of iterations on so it's better to decide that anything set aside K, because then you can cut it off before it tries to find a set that's arbitrarily large.
This is not correct, but I think what you have in mind might be correct because you're saying a thing was cutting off in time. I think you might mean the right thing. Any other suggestions? Yeah. Yeah, exactly. That's correct. So if your job is to decide if your graph has an independent set of size at least 5, you just optimize and you find the maximum. And if your maximum is at least 5, you say yes. And if it's not, then you say no. So because optimization really solves in this case the decision version. How about the other direction? Does the other direction work? If we can solve the decision version, can we use the decision version or an algorithm that solves the decision version as a black box for solving the optimization version? Yeah. So you're right that we have to solve sort of many or several versions here. It's true, but you don't need to record or backtrack anything. Or maybe any other suggestions for how to solve the optimization with a black box for an algorithm that solves a decision version? Yeah, that's one way. So you just try, because you're effectively trying to find the largest k for which the answer is yes. And you could do this using, for example, I mean, the way you proposed is one way. You just start at the largest possible. The answer might be no, so you just go down until first time the answer will be yes. And this is the largest k. And then you have solved the optimization version. You could also do a binary search over this might be more efficient, a binary search over k, just to find sort of the largest k for which the answer is yes. And this is the answer to the optimization version. So the largest k for which the answer is yes is the solution to the optimization version of this problem. Okay, and here's the second problem. The second problem is satisfiability, and this is sort of a more general form to what we have introduced as Horn formulas before. And we said Horn formulas are very easy to solve. We had a greedy algorithm that does that for us. Satisfiability, as you will see, is a bit more difficult to solve, or much more difficult to solve, because it is more general, and it's not restricted in particular to this very specific form that these clauses and Horn formulas take. In a general satisfiability setting, we allow general Boolean formulas, and we consider here, in particular, Boolean formulas in so-called conjunctive normal form. And a conjunctive normal form is simply this won't resolve it, a conjunction of clauses where each clause is a disjunction of literals. Let me just show you an example. I think that's easier to see before I introduce all these terms. This is a Boolean formula in conjunctive normal form, because we have, in this case, 1, 2, 3 different clauses shown here in these brackets. We have a conjunction of these clauses because of these ands. So we combine all these clauses in ands. This is at this point similar to Horn formulas. In Horn formulas, we also had a conjunction of multiple clauses, but every clause had to take one of 2 forms. Here we have a form that simply says that you can have all disjunctions. So you have literals of positive or negative variables, and their disjunction of all these variables. So this is a conjunction of a conjunctive normal form. So if you map this to the definition, the first term is clauses. Clauses are shown here in these brackets. I have conjunction of clauses, so all these brackets are connected by an and. And each clause is a disjunction of literals. So disjunction, you see that you have all these ors within brackets. And the literal is a variable that is either positive or it's negative. And if it's negative, it's indicated by this what's it called? A minus or a dash, a top, how do you call this? The symbol? A top bar? Okay, but a bar on top of the letters. This is how we indicate the negative of a variable. And every literal is either a positive or a negative variable. All right, so this is a Boolean formula in conjunctive normal form. And here's a special case. And we'll see that this special case doesn't make it much easier for us. A KCNF, I would just say CNF for a conjunctive normal form from now on. A KCNF is a CNF where each clause contains exactly k literals. Okay, here's an example for k equals 3. I have again a Boolean formula in a conjunctive normal form. And every clause in this case, they have the same shape. We have ands between clauses and ors within clauses, but I only have exactly 3 literals in every in every clause. Before you saw that we had some with 2 here and some with 4. Here, every clause has exactly 3 literals. It's a definition of, I actually didn't tell you the problem yet. So this is just our input. And now, based on this input on a formula with in conjunctive normal form, the satisfiability problem, or simply SAT, is a problem where we are given such a CNF phi, and we decide if the formula is satisfiable, meaning if there exists an assignment to all the variables such that the Boolean formula is true. So that's the satisfiability, or SAT, and K-SAT, or K satisfiability. It's the same idea, except that you're given a K-CNF, and you need to decide if this formula is satisfiable. So if there exists an assignment of Boolean values to all your variables that makes that formula evaluate to true. Is the problem statement clear to everyone? Good. And so what I want to show you now is a polynomial time reduction from 3-SAT to independent set. Meaning I can, I'm claiming here that I can solve the 3-SAT problem by using an algorithm that actually solves the independent set problem. And that's pretty cool, because it's really completely different problems. It feels one has, you know, Boolean variables and formulas, and I need to define if there's a satisfying assignment. In the independent set, I'm given a graph, and I have nodes and edges, and I need to find an independent set of nodes. It sounds very different, but in fact, what this theorem will show that we can actually solve 3-SATs once we can solve independent sets. And I'm not going to go through the formal proof. I just want to give you the main idea of this reduction. So, and for this reduction, it will help to think about what it really means to solve the satisfiability problem. So here's a formula with for 3-SAT. We have 3 clauses in this case, and each clause has 3 literals. So in 3-SATs, the 3 refers to the number of literals, not to the number of clauses. It's just a coincidence that we have 3 clauses, or yeah, in this example. And the way to think about how you solve this is that you pick essentially in every clause exactly 1 literal. You can pick more, but at least 1 literal you will have to pick that you decide to set to true. Okay, so you pick in every clause, you have to pick 1 literal that has to evaluate to true. Why is this the case? Because A, we have a conjunction, so we have and. That means that we have to make every single clause true. And to make a clause true, we have to make at least 1 of these literals true, because it's a disjunction of all these literals. So I have to pick 1 literal in every clause that I will have to set to true or false in case I'm picking a negative variable. So 1 literal in every clause has to be set to true. So why could I not simply do that? So if I would just say, well, I start with the first clause, I pick 1 variable, I set x1 to true, I go to the next one, I set x2 to true, and I go to the next one and I set x3 to true. So that seems to be like a really easy problem, or easy algorithm. It would obviously run in polynomial time. It would be really easy to solve this. Why does this not work? Yeah. Yeah, I mean, it might be a problem in this particular case, but I could always pick a negative literal in every clause. I think you're going in the right direction. Maybe it's maybe too specific for this example. The problem is that you might introduce conflict. So you might choose, and that's maybe what you meant, if I choose an x1 here and I treat every clause independently, at some point maybe I make a decision and pick, for example, yeah, maybe if I come to this clause and I forgot what I did here, and I picked x1 here, then I might pick not x1 here in this third clause. And if I do this, then there's no way for me to make both x1 and not x1 happy at the same time. So there's this dependence between different clauses. I cannot pick a variable and its negative in two different clauses. So now you could say, well, then just don't do it. Just don't pick one that is sort of a negation to a previous one. But that might cause that you're running out of options once you're reaching the end. And it doesn't mean that no such assignment exists. It just means that based on decisions that you made before, maybe you ran into trouble. So this is why this strategy doesn't work. And this is why you have to be a bit more careful. And you have to make sure that you don't introduce any conflicts, meaning in the sense that you cannot pick X from one clause and not X from another clause. Okay, here's a good example. This is how it would look like if I pick, for example, X1 in the first. This is a literal here in the first clause, X2 in the second, and X3 in the third one. This works because I could simply set all these three variables to true, and that would satisfy the assignment or satisfy this formula. Here's a counterexample where I would introduce such a conflict. I would, for example, pick X1 in the first, not X3 in the second, and then X3 in the third clause, and this would clearly introduce this conflict where I cannot sort of make both at the same time evaluate the true. And now the goal is to use basically independent sets and encode this, what we have just observed here, this idea of picking one in each clause without introducing any conflicts. This is what we try to encode as an independent set problem. And sort of the ingredient is there. Maybe you can sort of feel this already, because the conflicts here correspond somehow to having two nodes that are connected by an edge. So this is something that you cannot do in an independent set. So whenever you try to avoid selecting two nodes, you just introduce an edge between them, and you know that you cannot pick both of them in an independent set. This is just sort of the general idea. But I'll show you how we do this. I'm not going to give you a formal description how we construct such an independent set. I'll just give you one example, and this example will, I think, describe the intuition very well. So let's say that we're given this again, this Boolean formula in CNF. We would construct this graph that contains one triangle for every clause. So we introduce for every clause one node, and every node basically corresponds to one literal. So X1 here corresponds to this node corresponds to this, and this to this. Here, similarly, X1, not X1 corresponds to this, X3 to this, and X5 to this. So I have one node for every literal, and for every clause, I connect all these three nodes by an edge and make these triangles. Okay. So by this alone, what have I achieved so far? How many nodes can an independent set pick in every triangle? Remember the definition of an independent set? How many nodes can an independent set pick in each triangle? One. Exactly, because as soon as you're picking one, there's no second nodes that you can include without introducing this conflict, because they will be connected through an edge. So you will be able to select exactly one node in every triangle, which in our interpretation means that we aim to select exactly one literal in every clause. This was our way of thinking how to solve the satisfiability problem. So we're able now to select exactly one node in every triangle, meaning one literal in every clause. And how do we take care of these conflicts between different clauses? Well, we introduce an edge in this graph between nodes that are in conflict. So in this example, here I have X1 in this clause, and I have not X1 in the third clause, so we'll introduce an edge from here to here. And I have X3 here and not X3 here, so I'll introduce an edge also between these two nodes. And I have, again here, not X3 and X3 here between the second and the third clause, so I'll also introduce an edge between the second and the third triangle. And what that means now with these conflict edges is that whenever I pick X1 in an independent set and include it, I cannot pick any other node in the same triangle, but I can also not pick that node X1, not X1 in this triangle, because they are connected through an edge, and an independent set can pick at most one of them. So this is how I'm encoding this conflict between different clauses, simply by an edge between the two corresponding nodes. So what would be an independent set in this example? Can someone tell me an independent set? Any suggestion for an independent set? Well, let me first ask, how big should the independent set be such that we can conclude that the formula is satisfiable? Three, exactly. So we have that the independent set has to have size 3, and exactly then it means that we can satisfy the formula. So maybe let's look at an independent set and then I'll explain why. Can someone give me an independent set of size 3 in this graph, if it exists? Yeah. X1 in the first here, and X5. So you picked one node in every triangle, which is fine, and none of the 3 vertices between the triangles is connected through an edge, so this would form an independent set. The size of this independent set is 3, and that means that the formula is satisfiable. I don't know what example I have here. Yeah, except for the first one, it's the same independent set. So I picked here X2, which is the same as this node here, and X5 in the last triangle. In this particular case, so if I pick X2 here, and I pick X4 here, and X5, it's also an independent set. Yeah. So in this case, we have a lot of possibilities. The only things we can't do is, for example, pick these 2, or these 2 at the same time, or these 2 at the same time. Otherwise, we're free to pick any node here, here, and here. Yeah. I mean, most of the problems we dealt with were sort of formulated in a graph network. It's true for many problems. I mean, especially a graph is a very general abstract structure where you can formulate many problems in graph theoretical terms. But there will be a specific property that will come into this class that makes this actually particularly interesting. So it's interesting for a very specific kind of problems, these kind of reductions. And so to conclude this year, what we're trying to say is that a formula using a formula with k that has k clauses is satisfiable if the instance that I'm creating here has an independent set of size equal k. And this is now you would have, I mean, to prove this formally, you would have to prove both directions. But I think the intuition is clear that whenever this is satisfiable, you can create such an independent set of size equal k, not greater or equal to k, but exactly to k. And the other way is true too. If you get an independent set of size k, this can be only done by using 1 in each triangle, and therefore you're basically making 1 literal in every clause happy, and then the formula is also satisfiable. So there's a 1-to-1 correspondence between these two directions. Yeah. So, and this is what I said. So once we have colored these circles, we can again read out. This is basically the way we described a polynomial time reduction. Once we have run our black box algorithm X, in this case independent sets, we spend some polynomial time in transforming the solution to this one, which is simply a set of nodes, into a solution to our original problem Y. in this case, which is in this case is just an assignment of true and false values to our variables. And also you saw that you know, generating this graph takes also polynomial time. It's not much larger than this formula here. So we have polynomial time preprocessing, then we have some algorithm solving this problem, the independent set, and then we have some polynomial time post-processing to obtain our the solution to our original problem. So this was the first ingredient that we need in this class. This was this polynomial time reductions. And the second ingredient we need is sort of the class of problems that we're interested in. What we have studied so far fall into the following formalization. So we have in this class mostly looked at problems for which there exists an algorithm that runs in polynomial time, such as shortest path, minimum spanning tree, maximum flow. So all these problems had polynomial time algorithms. And for those, we can try to formalize this class of problems by first saying, well, an input, meaning an instance to your problem, a graph or whatever it is. Yeah, I think most problems, or sorting a sequence of numbers, that your input is somehow encoded as a binary string here. And then we define a decision problem. So in this context and computational hardness, we're dealing with decision problems X. We identify such a decision problem X simply by the set of strings, our inputs, the binary encodings of instances, on which the answer is yes. So meaning an independent set of size at least k, for example, for the problem of deciding whether the graph, a given graph, has an independent set of size k. So whenever the answer is yes for such strings, this set of strings for which the answer is yes is actually this is what we define a decision problem. So in this context, a decision problem is really a set of strings. And then an algorithm for a decision problem will get such a string as input and will output yes or no. So the algorithm gets a graph and a k, and it will say either yes or no. And if this algorithm does this right, we call this algorithm, or we say that the algorithm solves X if for every input, every binary encoding of an input S, the answer is yes, if and only if this string is actually a yes instance, meaning that it is an element in X. So whenever your graph has an independent set of size at least k, and only then the algorithm will actually say yes. So this is what it means when an algorithm solves X. And the algorithm has a polynomial running time. If we have such a polynomial P, such that for all S, the algorithm terminates on that input S in at most O of P of S many steps. So this is something that you're already familiar with, except for this formal identification of decision problems by a set of strings. But other than that, it's pretty much exactly what we have dealt so far with in this class. And this is what we call P. So the class of all problems for which there exists a polynomial time algorithm that solves problems in P is our computational class P. So all problems for which there exists a polynomial time algorithm. And this is true so P contains all these problems that you have considered so far: MSTs, max flow, set cover. We'll see later maybe that this is a counterexample. It's not. We don't know if there is a polynomial time algorithm, but for most of the algorithms that you dealt with in this class, these are algorithms for problems in P. So this is our first computational class. So not very interesting yet. It gets more interesting now when we're trying to contrast solving a problem with checking a problem. So let me try to first introduce this. So let's say if you look at independent sets, I'll tell you later that finding an independent set is very difficult. So solving this problem, or if you think of the decision version of independent sets, it's very difficult for an algorithm to decide if there exists an independent set of size at least k. So solving this problem is very difficult. But one good thing about independent sets is that once you give me some certificate, meaning a set of nodes, it's very easy for me to check that this is actually an independent set of size at least k or not. So checking a solution, it might be very difficult to find a solution, but once you find it, it's very easy to check that this is actually a solution. Okay. So and this is so the theoretic concept or the formal concept here is a so-called efficient certifier B. So an algorithm B is an efficient certifier for a problem X. If B is a polynomial time algorithm that takes, in this case, two inputs. So in contrast to the previous case where an algorithm solves a problem, a certifier takes two inputs. It gets the input, so the graph and K, and it also gets a certificate T. And now here's the interesting part, that for all inputs, this input is in X. So in this decision problem, if and only if there exists a certificate, a string T, such that B, the answer of your efficient certifier is yes. And on top of that, so maybe ignore this for the moment, the certificate cannot be too large. It has to be bounded by a polynomial in S. And P is, P is the polynomial. But the critical thing is that for every input, there must exist some certifier, a certificate, T, such that the answer of your certifier is yes, if and only if that input is a yes instance, meaning if it's an element of X. So in our independent set example, what that means is that an input, meaning a graph and a K, is in X, meaning a yes instance. So yes, there exists an independent set of size at least K. So the answer to this thing is to the input is yes, if and only if there exists some certificate such that B based on S and T is yes. So there must exist in this particular case a set of nodes that is independent and of size at least K, such that you can check and B will check this and will answer yes. So I think the next is an example. Yeah, here is actually the example that I just mentioned. So three sets, a certificate no, actually I mentioned independent sets. So for three sets, the certificates would be simply a false true assignment to your variables. Right? So if you plug in sort of this into the definition, let's forget about the first part. This is clear. So you get two inputs. B runs in polynomial time. You get input meaning this instance, this formula. This is S. And T is their certificate, in this case, just an assignment. And S element X, meaning this is satisfiable if and only if there exists a certificate, meaning an assignment, such that B of S and T is yes. So once you give this input and this assignment to a certifier B, it will be able to check that this is sort of the solution to this in polynomial time. And also this certificate is not too large. In this case, it's very small. It's just an assignment of values to these individual variables. And this is what it means if you have an efficient certifier. So given an input to a problem and given a certificate that sort of contains evidence for this input being a yes instance, the set certifier will say in polynomial time yes. Does this make sense to everyone? Let me maybe one more example. Yeah, independent set, that's what we just said. In this case, the certificates. There's a question. That's a very good question. We will come actually to a problem. I mean, that yes, no, sorry. This is there. This exists. This is not a trivial thing. If you ask sort of the question, if you ask the reverse question, so is a given Boolean formula not satisfiable? So if you flip these things around, it will be difficult to come up with a certificate that proves that your formula is not satisfiable. So it's not a trivial definition that there is no such that such a certifier exists. Yeah, but it's a good question. And for independent set, a certificate we said is simply a set of nodes. So whenever your input is a yes input, meaning there exists an independent set of size at least k, there exists a certificate, namely a node, a size of or a node set of size k that is independent, which the which this verifier, certifier can check in polynomial time and answer yes. Okay, does this make sense to everyone? So the difference between solving and checking. So solving might be very difficult, but in many cases, even if solving is very difficult, checking might be very easy. Now, we could, in principle, use such a certifier to solve a problem, because we said T, the certificate, is sort of polynomially bounded in the size of the input. So we could simply enumerate all possible T's and then run our certifier. And whenever we find one T for which the answer is yes, then we know that the answer is yes. So then we solve this problem basically by running this certifier on many T's. And whenever there's one T to which it says yes, then the answer is yes. Then we have solved the algorithm at the problem. But of course, enumerating all possible T's will typically take exponential many steps and cost to this algorithm. So this doesn't give us immediately an efficient algorithm for solving the problem, but in principle, it does give us an algorithm to solve the problem just based on a certifier. But we don't know how to solve it yet efficiently. And now, based on this definition of certifying a solution, we define the computational class NP, which is simply the class of all problems for which there exists an efficient certifier. So most problems, or probably all problems that we discussed so far, have an efficient certifier. They're all in NP. And now comes sort of a central lemma, namely that P is subset of NP. Can anyone explain why that is true? So why is every problem in P in NP? Yeah. Yeah, and how do you do this? How do you use it? I mean, it's correct. How do you use it as an efficient certifier? Because you have this certificate T. What do you do with T in the certifier? So you have to build a certifier that takes S and T. So what do you do with T? No, you could just ignore it, right? You don't have to do anything with T. So the algorithm that solves this problem, you can use it as a certifier by just ignoring T. So you just take S and then answer the question for S by just ignoring T. You don't need to care about T. And that's why every problem that you can solve in polynomial time can also be checked in polynomial time. You just don't care about the certificate. You solve the problem, and solving this problem is the same as really checking it. It's not the same. It's actually typically harder. But for problems for which there exists a polynomial time algorithm, this is what you get for free, essentially, a certifier. So this is what this proof says, that for any problem P with an algorithm, we construct a certifier that just returns A of S. So it returns S, A of S, meaning it says yes whenever S element X. And that means also there exists a T for which B says yes if S element X. So this is just a sort of a formal technicality. And you can easily, we already said this, that 3-sat and independent set are both an NP, because we can verify or certify a solution very efficiently simply by looking at a set of nodes or an assignment that has a certificate. But we can't prove that they require more than polynomial time to solve them. So we know that they are in NP, both of these problems, we don't have an efficient algorithm for them. We don't have a polynomial time algorithm, neither for 3 sets nor for independent sets. But we can't prove that no such algorithm exists. And this is the tricky part of this. And this is what leads us to the following. So here's the sort of a fundamental question in actually computer science that's been open for many, many, many years now. Is P equal NP? So is there a problem in NP that is not in P? This is, we still don't know this. So is there any problem for which there's that we can check in polynomial time, but we can't solve it in polynomial time? So we don't. 3 sets and independent set are examples that we know there are in NP. We don't know, or we don't have any polynomial time algorithm, but we don't know if no such algorithm exists, or if we just didn't find them yet. So we don't know if P is equal NP. So, and since we don't know this, what researchers have been doing for a long time now is try to find sort of the hardest problems in NP. So this is categorized or formalized using this notion of NP completeness. So we say that a problem X is NP complete if A, it's an NP. So X is a problem in NP. So we have an efficient certifier for this problem. And for all other problems in NP, we can reduce all these problems to X. So all problems in NP can be reduced in polynomial time to my problem X. This is what it means to be NP complete. So I think now we'll in a minute see why this means that this is the hardest problems in NP. Because of this, really. Because now, if an NP complete problem can be solved in polynomial time, then P is equal NP. In this respect, NP complete are sort of the NP complete problems and are the hardest problems really in, or the most difficult problems in NP. Because if you can solve any of them in polynomial time, then actually P equal NP. Then you can solve all of them in polynomial time. And why is that? Why is this lemma true?